In this video, I want to look at how midpoint Riemann sums look inside sigma notation. So we need to start by reviewing the definition of the Riemann integral in terms of Riemann sums one more time. Riemann defined the integral between a and b of f of x dx as this messy looking limit where delta x is b minus a over n and ck is trapped between these two numbers. What I want to do is I want to remember that what we are really looking for is understanding of what's going on, and f of ck times delta x is nothing more than the area of rectangle K. And delta x is the width of all of our rectangles because we are subdividing the interval that we are integrating over into n equal width subintervals. And the interval that we are integrating over is the interval between a and b. ck is a sample point in the kth subinterval, and the kth subinterval runs between xk minus 1 and xk. And as we have previously seen, xk minus 1 is equal to a plus k minus 1 times delta x, and xk is equal to a plus k times delta x. Since we are looking for a midpoint Riemann sum, what we want to do is we want to let ck be the midpoint of the kth subinterval. So I need to find the midpoint of the interval between xk minus 1 and xk. So let's do that on this panel. I want to find the midpoint of this particular interval. Well, let's see, we've called it ck, and ck is going to be the sum of the two endpoints of my interval divided by 2. In other words, I average the two endpoints. And xk minus 1 is a plus k minus 1 times delta x, and xk is a plus delta, k times delta x. And we have to divide everything in sight by 2. So now it's time to do some algebra. We have an a there, we have an a there, so what we've got is 2a, and then we've got k minus 1 times delta x plus k more times delta x, so we have k minus 1 plus k times delta x, and we do still have to keep our denominator around. Now, when I look at this, I've got 2k minus 1 inside that set of parentheses, so I'm looking at 2a plus 2k minus 1 times delta x all over 2. And I can rewrite this as 2a over 2 plus 2k minus 1 times delta x over 2. And when I think about what's going on here, I realize that ck is going to be a plus k minus 1/2 times delta x. And I need to simply plug this in to the Riemann Sum Formula. And when we do that, this is what we get. Our midpoint sum is going to look like the following. We're going to have the sum as k goes from 1 to n of f of, and this is tricky, so I'm going to use some color to help keep the parentheses straight. And ck, we showed, was a plus k minus 1/2 times delta x. And now I have to multiply that by a delta x. And the stuff inside the big parentheses is f of ck times delta x. So that's what's inside these big parentheses. Let me make that just a little bit clearer. So f of ck times delta x is this mess, and there's the summation. Now, this would be a perfectly decent formula, but there is something that I want to point out. That minus sign creates problems when we try and use this formula to do specific problems, because then we have to go chasing plus minus signs. So most textbooks, including our textbook, do a change of counter variable to rewrite this particular sum so that that minus sign goes away. And here's how we do it. We are going to let k equal L plus 1. And the reason I want to do that is that k minus 1/2 then becomes L plus 1 minus 1/2, which simplifies to an L plus 1/2. So this chunk here is going to be replaced by L plus 1/2. But if I'm going to replace that by L plus 1/2, I also am going to have to change the counter to L and change the endpoints on my summation sign. Well, if k is equal to L plus 1/2, then k minus 1 is equal to L, and when k is equal to 1, L becomes 1 minus 1, which is 0. So our new summation is going to start at 0. And when k is up here at n, L is going to be at n minus 1. So our summation is going to be a summation as L goes from 0 to n minus 1. And our new midpoint formula So our new midpoint sum is going to look like the summation as L goes from 0 to n minus 1 of f of the ck is now going to be equal to a plus L plus 1/2 times delta x in that f of, and now we have times a delta x and then the big parentheses. So to understand what's going on in this formula, we have f of what used to be our ck being written as a plus L plus 1/2 times delta x, and then there's the delta x from the Riemann sum. So in other words, this stuff here is what used to be our f of ck times delta x. So that's what this stuff here is. Now we could use this, we could leave this summation as an L, but most books then go back and do another change of counter variable, and they say it doesn't matter what I write this particular sum as, and so the formula given in our book looks like this. The midpoint sum is going to be the sum as k goes from 0 to n minus 1 of f of, and I do still want these parentheses around, a plus k plus 1/2 times a delta x, and let me make that 1/2 just a little bit easier to read, times the delta x, and now we're going to add all of those guys up. And so the stuff inside this square brackets is our f of ck times delta x. This is worth writing down in your notes as our major midpoint sum formula. What I want to do next is look at a specific example using this formula to find what midpoint sums would look like as Riemann sums. So what I now want to do is I want to write the midpoint sums for the integral between, let's make it between 2 and 5 of x squared dx, where we're going to use n equal 5, 10, and 20 middle rectangles. Middle rectangles are the ones that use midpoints for their height. So what I want to notice is I want to note that my midpoint sum formula is going to be the sum as k goes from 0 to n minus 1 of f of a plus k plus a half times delta x and then times another delta x. So it's f of this mess times a delta x. Now I know that a is going to be something and delta x is b minus a over n, so delta x is something. And these things come directly off of the integral. The bottom endpoint gives me the a, and the top endpoint gives me the b. So a is going to be 2, and delta x is going to be 5 minus 2 over n. It's going to be 3 over n. So now I'm ready to simply substitute in for my midpoint sum. So my midpoint sum is going to look like the sum as k goes from 0 to n minus 1 of f of, let's see, a was 2 plus k plus 1/2 times delta x, which is 3 over n, and then times another 3 over n. Now it's useful to change these parentheses color to make it clear that I've got f of this nasty mess times that 3 over n, and this 3 over n is a constant as far as the summation is concerned, so it comes out of my summation. And what I am now looking at is that my middle sum is going to look like the summation as k goes from, well, actually I need to pull that out. So let me write that thing out. We pulled this out, and when we pull it out, we get 3 over n times the sum as k goes from 0 to n minus 1 of f of 2 plus, and I want to kind of clean this up just a little bit. That can be rewritten as, let's see, how do I want to rewrite that? That can be rewritten as 3k over n plus 3 over 2n, simply by doing k times 3 over n and 1/2 times 3 over n. So we get that. And then the 3/2 has already been pulled outside. And now what I need to do is I need to think about how I want to square this, because f of x is equal to x squared. And what I'm going to do is, I think what I want to do here is I want to get a common denominator so that I'm actually going to be looking at a binomial. So our middle sum is going to be 3 over n times the sum as k goes from 0 to n minus 1 of f of 2 plus. The common denominator here is a 2n, so we're actually looking at 6k plus 3 over 2n. And now I can actually square this, and when I do, my middle sums become 3 over n times the sum as k goes from 0 to n minus 1 of 2 plus 6k plus 3 over 2n, quantity squared. Now, we have to figure out what the heck that is. our middle sum is going to be 3 over n times. The sum is k goes from 0 to n minus 1 of. Well, if this is a binomial, and when I square it, I'm going to get the first thing squared, which is a 4, plus 2 times the first term times the second term. Finally, I get the second term squared. And that ends what f evaluated, what that thing squared is. And now I simply need to do a little bit more cleaning up, and then I'll be ready to plug my 3 values of n in. So my middle sum is now going to look like 3 over n times the summation is k goes from 0 to n minus 1 of 4 plus. When we clean this up, we're looking at, well, let's see. One of those twos cancel, and we've got 12k plus 6 over n, and I'm just going to leave that as 6k plus 3 squared over 4n squared. And now I have something that I can actually plug the values of n into. So when n equals 5, our author writes the middle sum for 5 rectangles is capital M sub 5. That will be 3/5 times the summation as k goes from 0 to 4, because n minus 1 will be 4, of 4 plus 12k plus 6 all over 5 plus 6k plus 3 quantity squared over 4 times 25. And I'm just going to leave it like that. I could do some more simplification if I wanted to. When I look for the middle sum for 10 rectangles, n is now equal to 10, and this is going to be 3 times 10 times the sum as k goes from 0 to 9. 10 minus 1 is 9. And we will have 4 plus 12k plus 6 over 10 plus 6k plus 3 quantity squared over 4 times 100, because 10 squared is 100. And our final one was n is equal to 20, so our middle sum for 20 rectangles is going to be given by 3 over 20 times the summation as k goes from 0 to 19, because 20 minus 1 is 19, times 4 plus, rather of 4 plus 12k plus 6 over 20 plus 6k plus 3 quantity squared over 4 times 20 squared would be 400. And so those would be the 3 expressions that we would be looking for answers for our problem.